Assalamualaikum warahmatullahi wabarakatuh. We are from Group E, Section 2. Today we will present about hyperparameter tuning of ADA-boost using genetic algorithm. So let us see what are the contents that we will discuss after this. The first introduction of ADA-boost, implementation of ADA-boost, hyperparameter tuning, evaluation of ADA-boost performance, and multi-class classification using ADA-boost. For the introduction of ADA-boost, ADA-boost combines weak learners in sequence. Each learner focuses on fixing errors from the previous one. After training, learners get weight based on their performance. The final prediction is based on the weighted votes of all learners. Arabus assign weights to all training instances. Initial equal, the weights increase for misclassified cases and decrease for correctly classified one. This helps the next learner focus on harder cases. A weak learner's weights in the final model depends on its error rate. Lower error means higher weight. Weak learners are simple models that perform slightly better than random guessing. Arabus combines them to perform a strong model by focusing on misclassified cases and improving accuracy over time.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sophia. So I'm going to explain about the implementation of AdaBoost. So as the summary, first we're going to train the AdaBoost on a synthetic dataset using a weak learner. Here as a weak learner, we're going to use decision tree classification with maximum depth of 1. And then the number of estimator is set to 50. Learning rate is 1.0. Then we're going to split the training to 70% and 30% to testing. And finally, we're going to set for random state to 42 for the reproducibility. Now moving on to the code explanation. First, we're going to import all the necessary file, and then move to our very first step is to generate the data using make classification function. Here the function will automatically create a fake data set with 1000 sample, 2 features and 2 classes, which is binary classification, class 0 and class 1. The second step is to split the data into 70% for training and 30% for testing. And then for the random state, we set to 42 to make sure that the code, the data set will be split the same every time we run the code. And then for the third step, we define the weak learner. Here we're going to use decision tree classification with the maximum depth of 1, which means it will only split once, and is a very simple learner to do very well and classify the data set on its own. Step 4 is to create and train AdaBoost. Here it uses the weak tree as a base, which and the estimator is set to 50, which means it will build 53 with only one split. Each time it will fix the error of the previous tree, and then fit the trains it on the training data. For step number 5, evaluation, it tests the model on the test data. Then the score was 0.88, which means 88% of the test data was classified correctly. Now, question 2.2, visualize the decision boundary of the train model. First, we're going to define a function named plot decision boundaries, and then we're going to define the grid for the plotting. So we're going to find the minimum and maximum of the data and extend it by 1 unit for the padding. And then we're going to make a mesh grid with a spacing of 0.01. For the third step, we're going to predict class for each grid point. So here XX and YY are in 2D list, 2D array. By using rival function, we're going to turn them into 1D array. And then we're going to use np.c to stack array side by side, which means it will become from for example, x1, x2, x3, y1, y2, y3 into x1, y1, x2, y2, x3, y3. And then the model.prediction will return a long list of prediction class label. So after that, we're gonna reshape the prediction. So here the prediction are in the 1D list. By using reshape function, we're gonna reshape it back into the 2D list. For step 4, we're gonna plot the decision boundaries. We use plt.contour to fill in the color for each class, and then plt.scatter to plot actual data points on top of that. So here we can conclude that data boost visualization prove how the boosting turns simple or weak learner into a powerful model that can give a flexible and accurate decision boundary or result.
Next, we move on to hyperparameter tuning. Generic algorithm is implemented to tune the hyperparameter to optimize the end estimator and learning rate. To use the deep library, cross-validate to evaluate model performance, provide the final optimized hyperparameter. This is Adabus model is run with the hyperparameter obtained from the generic algorithm and evaluate the test accuracy. The performance of the model is compared before and after hyperparameter tuning.
All right, so moving on to the next question, which is question 4, which is about evaluation and reporting. So the question 4.1 asks us to analyze the performance of ADA boost before and after hyperparameter tuning using the genetic algorithm. So the first question is about the improvements that we observe after tuning the hyperparameters, and the second one is about how does the performance of the ADA boost model change with different values and of n estimators and learning rate. All right, so about the improvements that we observe after tuning the hyperparameters, based on the result, the initial model performance shows that the accuracy of 0.88, but then after the optimized model performance, it increased to 0.89. Um, and estimators is increased from 50 to 185, and the learning rate increased from 1.0 to 1.44. So the improvement that we can clearly see here is the accuracy increased by from 0.88 to 0.89. It increased by 1%. So it demonstrates that the hyperparameter tuning can also enhance the model performance in general. Okay, so moving on to the performance of the Adabus model change with different values of n estimators and also learning rate. Right, so the first one is n estimators, or we call it as number of weak learners. Okay, so the model was able to learn more intricate patterns by increasing the number of weak learners from 50 to 185. But then, if meanwhile the if we increase the number of learners from 50 to 185, this could decrease bias and increase accuracy. But if we excessively change the and estimated value to large value, however, it may result in overfitting and increase computational expenses. Okay, so moving on to the learning rate or contribution of each learner. So each week learner's contribution to the ensemble was successfully adjusted by the customized learning rate of 1.44. While a greater learning rate runs the danger of instability, a lower rate could converge too slowly. So this genetic algorithm helped to discover the ideal equilibrium of this model. All right. So next is 4.2, which is to discuss the potential limitations of using genetic algorithms or GA for hyperparameter tuning, and when would we consider using alternative optimization techniques like grid search or random search. Right. So the potential limitations of this particular algorithm is the first one is computational cost. Why? Because the genetic algorithms evaluate multiple individuals per generation across multiple generations. So, for larger data sets or models with long training times, this could be more expensive, and it could increase the cost eventually. Next is stochastic behavior. What is stochastic behavior? This is what we call when the results can be vary between runs due to the randomness in initialization, mutation, and crossover. Next is complexity of setup. So why it become more complex is GA is require us to carefully tuning with their hyperparameters, such as population size, mutation rate, and also number of generations. So these could resulted in the more complex setup. So the last one is overfitting risk. So tuning hyperparameters extensively without proper validation may lead to overfitting the training data. All right. So next is the alternative optimization techniques. So the first one is grid search, and the second one is random search. So grid search is the exhaustive search over predefined hyperparameter ranges. So, grid search is best to use for small hyperparameter spaces, but computationally expensive for large ranges. So, um, we use grid search technique to when the hyperparameter space is small, but the computational resources are sufficient. The random search techniques is samples it samples random combination of hyperparameters. So this technique is efficient for high dimensional spaces and faster than compared to grid search for in terms of when you have large ranges. So we use random search technique is when you need faster results over a large hyperparameter space.
Hi, Assalamualaikum. And now move on to the last of the question, which is the bonus question. So, this question will be to implement a multi-class classification problem using the AWS algorithm and its hyperparameters using the generic algorithm. So, these would be the codings that we use as to implement each of the problem for multi-class classification. So what's the multi-class classification? So it is implemented using the AWS algorithm, which to tune using the GA algo, and this code actually can demonstrates how would be a dataset of iris with more than two classes. And moving on, which is on the dataset selection. So within using iris dataset, we use we take as a classical machine learning dataset, which is under more instances, which we choose as a representative flower, which is of four features, which is the septal length, sepal width, petal length, and also petal width. So under these classes, we separated into every each part of each, which is the Sentosa, Versicolor, and also Virginica. And also we put as the ADA boost in it as the train speed part of the code, and we got the result of the initial ADA boost accuracy, which is under the multi-class of 0.93, and that's all. Okay, so last but not least, on the second part of the bonus question, which is under the code, why was under hyperparameter using generic algorithm. So this will be the codes. So why hyperparameter tuning? So under this result, it's actually shown as 80% is good just because of the tuning from the previous of hyperparameters that actually can improve as in the performance. So as you can see, the result will be the number of estimators that is based on the weak learners, and also for the learning rate is how many that learners that contribute for the final model to find out of what is the result as the right combination of the two enhanced classes for the both accuracy and generalization. So on the last part of it is it the tuning and to evaluate the optimized model. As to we have run the hyperparameter tuning under the using of deep library, DEAP library, which is inspired as a biological evolution as to select and also crossover to augmentation that evolve its solutions under generations. So in this possible content, which is the codes itself, is the n estimators and also the learning rate. So under its results, it shows as for the n estimators is 185 and for the linear rate will be 1.44. And these results shows that the finite doubles accuracy after hyperparameter tuning will be the 0.96. So there will be some increase of 1% that will be benefit that shows as accuracy of the benefit of optimization. And the Adabus algorithm is actually strong and also can be improved from tuning so that it can be incremented unless the base learner or the data changes significantly. So with that will be it for my part and my group. That's all. Thank you.
That's all from us. We hope you enjoyed this presentation. Thank you.